Well, I see that quite a few people have joined, so I think I'm going to start. And for those who have just joined, my name is Dariia Porechna, and I work with blockchain team in Wolfram Research South America. Though I'm not in South America, but that's my team. And I'm working on cryptography functionality. So it's not just blockchain, it's a more general field, but we do provide basis for also our blockchain projects. And yesterday, Christian was doing a talk on blockchains, if you want to rebroadcast that. But I am doing cryptography, and cryptography in Wolfram Language has started around version 10, if I'm not mistaken, with things like encrypt, decrypt, decrypting of files, generation of keys, and another encryption algorithms. Then since then, we have grown quite a lot. You see that this list is only becoming longer. We have added digital signatures. We have added elliptic curves, keys, and signatures. And we have added file signatures, system credential, a lot of stuff. And since today, I'm going to be talking mostly about stuff that we've been adding for the last year since the last conference. And this is going to be almost everything new in 12.2. So the abstract you have already seen, it's been on the meeting page. So what's new in cryptography in 12.2 is that we have added more support for more elliptic curves, since the first one that we've added has done so good. We decided it's a good way to go. We have added another digital signature algorithm, which is Schnorr digital signatures. So now we have 3 different digital signature algorithms in total, which are RSA, elliptic curve, the standard elliptic curve ECDSA, and Schnorr. A big thing for new in 12.2 is going to be import of PEM files, and we've tried to do our best there, and I'm going to show you examples. And connected to that, a symbolic representation of certificates to make them computable and to make people able to do operations in Wolfram Language with certificates. So let's go. About elliptic curves. So in version 12.0, if I'm not mistaken, we have added elliptic curve cryptography to the Wolfram language. And we have started with this curve CCP256K1, which is probably one of the most famous curves that exist, because it's the one that Bitcoin is based on, and Ethereum, and a lot of other blockchains as well. So to support that, we have added key generation on elliptic curves, and the default, if you ask for elliptic curve, is going to be this one, because that's the one more used. And in 12.2, we have added a few more, and until the release, there might be a few more again. Right now, we have 6 different. So this one is 256 bits long. This one is a little bit longer and a little bit more secure, and then this one is twice as long. So if you want to set up a higher security, even the one that is used in Bitcoin, you can use this one. And to specify that, to generate a symmetric key pair, if you want to now be able to generate a curve with a specific name, you can just set the curve name option to this name of the curve. And it's going to generate, let's say, this one, which is longer. And there is also a shorthand notation without having to specify method goes to type in C1. You just say method goes to the curve name. And it's going to generate you a key pair of private and public key based on this curve with needed lengths and needed parameters. Now, once you have the keys based on this curve, you can just pass them to generate digital signature without having to specify any method here or curve name again. It's just going to automatically generate signature using the correct one that you have specified. So right now we only have 6 curves, and in the wild there are many more. I think OpenSSL supports around 30, maybe a few more, but we're going to get there. And so this is what's going to be available in 12.2. This next thing that is new is Schnorr digital signatures. And I think that has already came out in 12.1.1, but this wasn't announced in the last year's conference, so I'm saying it again. And for this one, I can actually use the keys that we have generated on the previous page, and you see it has automatically taken the curve from the key, but the type of signature has changed to Schnorr. And here it was type of signature elliptic curve in the bottom. And here is Schnorr. Once you specify type, goes to Schnorr. And Schnorr is the algorithm that was invented a couple of decades ago, but now it's gaining a lot of this fame because it's more secure than just the classical ECDSA, because you can prove it, it's probably secured, means you can mathematically prove that it's secure. And it allows for multi-party signing, which means that not only me with my private key, I can send this message, also that if there are 3 of us and we want to sign the same message, like for example, you know, when there are 2 of you and you're buying an apartment and you want to both sign the contract, Schnorr signatures are the only ones that allow to combine private keys in a way that creates a signature that is based and verifiable on all of these keys, which was one of the reasons for us to also add this to the Wolfram language. Then the big thing that we have been working a lot, which is the one that we have spent most time for this new version, is the import of PM files. And PM files are one of the standard ways of storing and exchanging of cryptographic data, which are keys, certificates, encrypted data, signed data, lots of things. And in 12.2, we're going to be able to import them in a very nice symbolic form. So just to give you an idea, the usual PM file, for those who don't know, looks something like this. So it has a title, begin, end. It says here it's a private key, and then it has the sort of encoded structure that is for humans absolutely ununderstandable, but it's an encoded sequence of bytes that have values. In one file, you can have multiple of those blobs inside, and Wolfram language can import all of them. The biggest that I saw, for example, in Linux, you can go to the repository that contains certificates in your computer and put them all in one file, and there's going to be like 200 of them, and Wolfram language can import them into like even file that big. So now I'm going to show you what this new version is able to do with this file. So magically in 12.2, a file that looks like this turns itself into a private key. The private key head that we use by default, you can go and see what's actually inside, what are the values that have been imported, and you see that from this blob, we've been able to understand that this is based on this curve And this is the public key, and this is the private key, that it is not uncompressed. And we have also provided them as a byte array for convenience. So now you have this file, and you might have gotten it generated from another program. You might have gotten it generated by yourself. And what's cool is that you can just import it and use it in Wolfram Language without having to use generate asymmetric key pair to every time generate a new session. Once you have this key saved, you don't have to worry that it's going to get lost. It's just there, and you can import it anytime you need it. You can compute its public key, and you've seen that in the file there was now public key, but you can easily compute it in Wolfram Language already, and now you can use them as a pair. For example, for signing, assume I have this file, I have created this document, and I want to digitally sign it by saying that it's actually me, the owner of this key, who was able to sign this document. And with generate file signature, I can do so, and it gives me a digital signature. And anyone who has my public key can just go and verify that is actually true, that I have signed this file with my private key. Now, as I've just said, I've said this phrase, I am the owner of this private key. And for you as viewers right now, there is no way to verify that. It's just something that I claim, which might as well not be true, because in the modern age of internet, nobody trusts no one. And so if you receive this file with the signature with somebody who claims to be me and says, oh, well, I have signed this file, this information, you can verify it, it's true, it's correct. You don't have to believe. And because of this problem, because remotely people were not able to actually prove that I am who I am claimed to be, and that this key is the one that I am claiming to be my key, emerged a thing called public key infrastructure and the thing called certificates. A certificate is a sort of proof that the party who's the owner of the private key is actually the ones that they claim to be. And that is usually verified by a trusted third party or a trusted agency. It can be a government agency, it can be a private agency that gives certificates to people. So this certificate, for example, let me show you what it is. So a certificate is a structured, standardized thing that has several standard fields in it. One very important field is actually who it was issued to. This was issued to a test client, not that exciting. By whom? By OpenSSL, test CA, and we assume we trust OpenSSL who has issued this certificate. It has a validity, so it's still valid, fine, and a lot of other useful fields. And this file looks exactly as the one that we have just looked at. It's a header and a lot of weird bytes inside. Some of them also have a blob on top. And in Wolfram Language, we are now able to decrypt, sort of decode this into this very nice structure. And you can query this object for a public key if you need it. You can query for its serial number. You can get the signature out of it. And you can compute with them anything you need. And this is a very specific piece of intended for supporting this sort of public key trust infrastructure between parties who actually do not trust each other, but with certificates they can. And just to preview how versatile we have made the subject to be, I'm going to show an example that is a little bit complicated, but it just showcases everything we need. So a certificate, just to give you an idea, this is a certificate from wolfram.com. And this is, for example, if you go to wolfram.com website and in browser you set this little lock, it's a certificate valid. And you go to details, the certification pass, and you see there is this certificate, that's the one above it in the chain. So this one is the authority that has issued the certificate to Wolfram, and then this the authority who has issued the certificate to that authority that has issued it to Wolfram. And we can import that. For example, when you say copy to file, we plan to do that directly from the URL, but so far you can import it as base encoded. But for your convenience, I have already copied this into this iconized little blob here. So it's quite a big one. It has 7,000 characters. So you're going to have it in the presentation notebook if you want to play around with it. And we are able to import all of them, the whole letter. And you can see that the first one was issued to Wolfram by GoDaddy Secure Authority. Then the one below it was issued to GoDaddy Secure Authority by GoDaddy Root Authority. Then the next one was issued to the root by GoDaddy Group Incorporated. And then the last one was issued by GoDaddy Group to GoDaddy Group itself. So the last one in the chain is called the root. And this whole thing is called a certificate chain. And now that our browser connects to wolfram.com, they receive this chain and they receive the certificate. They see that it's valid. And they know that connecting to wolfram.com is safe. That the wolfram.com website they were trying to connect is actually the one that it's claiming to be, and not some scam. It's somebody who tries to pretend to be wolfram.com that we don't have to trust. And just for the convenience, let's name them first, second, third, and root. So we don't have to do part every time. And let's just check that this chain is actually valid. And we can do all of that programmatically. For example, first of all, the obvious thing that comes to mind, let's check that every one of the states in the chain that says valid before, that every one of the valid before dates is actually after now, and that's true. So good, so far so good. We can check that certificates do in fact form a chain, which means that the issuer of the first certificate, and we can look at it. So it's United States, Arizona, Scottsdale, GoDaddy Incorporated has issued the certificate to Wolfram. And to form a chain, the certificates have to have that the second certificate as the subject, the one that has issued the first certificate. And we see that they're the same. So that's two certificates at least. Do you have form a chain of trust? And with things like moving map, we can just go trade. Good. They actually do form a chain of trust, which means that every next certificate is issued by every previous one. We can check. I see some questions coming in, and I think I'm going to answer them later after I finish going through this. So we can check that the last certificate is read, which for read, it's both the issuer and the subject. It certifies itself, and it's true. And what we could also see that in the extensions read, you see we can parse all the extensions. We can get the criticality flags. We can get the data where it's relevant to be binary, or where it's relevant to be an association, or where it's relevant to be just an integer. And in this case, we can see that this particular read has certificate authority goes to true. So it is an authority that can issue certificates, which is exactly what we expect to be, which is good. Then on to something even more complicated. You can query any field from the certificate. So to check that, we take the public key of the read. We can take the actual signed bytes, and let's just for a second look at the read. So this digital signature means that the read, the actual issuer of the certificate, has taken all the bytes of the certificate and they have signed this with this public key. And that's what they claim to, and that's what we're trying to check here. And it's cool that we have integrated all of this into our existing functions. So this returns as the digital signature, just the way that we use it internally. And you can actually just feed that to verify digital signature. It's going to tell you it's true. And we can also check that the same way for every certificate in the chain. Though for the other certificates, they have to be signed by the issuer. So for example, the first certificate has signed data, it has digital signature, but it has to be signed by the second one. So the public key comes from the second one. And this again we can do with the movie map that takes the signed data from the first one, signature from the first one, but the key from the second one, and just goes up the chain. And it gives us all true. And that's in many other wonderful things you can do with the certificates. And I have barely made it on time to leave you some time for questions. I can talk about this for hours. So feel free to keep asking in the chat later or shoot me an email. And you're going to have this notebook. You're going to have all the documentation for these things that you can go and read. So I think this documentation is already in the build. Yeah, so you can familiarize yourself even more. Now, there were questions. So there was one question here in Zoom. Is the support for key store planned? If you mean the key store as in system keychain, I think we do already have that. It's called system credential. And system credential creates a key that you can actually store. I'm sorry, I'm not aware about Java key store, but PKCS 12 files we are planning to be able to read. And but about Java, I'm not sure I can answer your question right now. How would I go about signing a notebook and embedding it in the notebook? So right now you'll have to just sign in a notebook and send the signature along with the notebook. It's not yet possible to embed it inside, but it's certainly something we are considering, but this would be a big project. So it actually has to be convincing to everyone because we need a front-end group and we need a lot of people to be working on it. But I'm glad you asked because that's sort of a project I'm trying to actually make live. And I think it's going to be very useful to people to be able to embed the signatures in the Wolfram files that they're creating. And right now we already have basically everything we need for that. We have the signatures, we have the notebooks, we have the hash, we have the actual things. So I think this actually has future and it might happen at some point. Right now, for example, if we are going to, here I was signing the file. So if I would publish this file to cloud, I can publish the signature along with it, and people can download, post them, and verify, by just getting cloud get from cloud object. But this is certainly something that I personally think should be done because it's going to be useful to people. Because we as Wolfram are a part of a lot of, research institutions. I mean, our users are part of research institutions, and I think it's going to be useful for them to be able to sign the files actually embedding their credentials. Are there any plans to have a system interchangeable private keys via Wolfram Cloud? Not yet, but we have to design that. This is a part of the saying of the previous question, basically. So to allow people to have a verifiable system of embedding their credentials into notebooks and having other people be able to check that, we will need to design this infrastructure inside Wolfram. But I'm going to get to ask because it's good to see that people are actually interested in that and might give us more fuel to actually go and do that project, because that is going to be a major one. Okay, and any last questions? Okay, then I think everyone has by now asked what they wanted. Please feel free to keep asking once you can get a chance to go through the notebook. And I appreciate your comments, and I appreciate suggestions about what people want to see in our cryptography infrastructure sort of in Wolfram Language, because that will give us more priority on which things we need to look at first and which direction we should keep developing our project. And thank you all for coming to my talk today, and enjoy the rest of your conference and enjoy. Thanks.